So I'm going to talk about high-frequency superconductivity, and I start with a disclaimer. This is probably not route immediately to high TC, so it's not more than proper that I'm out here on the outer track here on this road. But what I am going to tell you is that to understand actually a rather wide range of superconductors and superconducting system, it is important to know what high-frequency superconductivity is and how to think about it. So I'm going to try to spend my 60 minutes here giving you a brief crash course and then giving you a few more contemporary examples of this. So in more particular detail, this is the outline. So as I think a whole bunch of you don't really know what high-frequency superconductivity is, I'm going to tell you what it is and where we traditionally find it, and also how or why it becomes an high-frequency superconducting state. And then I'm going to talk about two projects we worked on in my group, and I choose these two because they illustrate what I think is they're showing that I think high-frequency superconductivity is going to be even more important in the future because it's very prominent in materials that are topological or that has multiple bands. So I'm going to talk about materials that are called nodal loop metals, and I'm claiming actually an optimal high-frequency Joseph-Sonnenschein, so I'm going to show you why. And then I'm going to talk about multiband system and start with a very simple two-band model and show how high-frequency shows up there. And then take that model and apply it to several different superconductors. So I'm going to talk about Sr2RuO4. I had meant to talk about uranium platinum 3 but the story is rather similar to Sr2RuO4. So I got inspired by the talks earlier today on the maticity to actually talk about some very recent work we've done on the topological insulator bismuth selenide, and I actually have a lot of strong, it has essentially dominating high-frequency pairing in part of the frequency range. But before I get started, let me just acknowledge people actually did a lot of the work. So the work on Veil metals inspired Boston Annica. Work on Multiband System has been these three people who have already left Uppsala, and work on bismuth selenide between Johan and Firebars. And in Sweden, nothing gets done without external funding, and for the high-frequency thing, especially grateful to the ERC. Okay, so what is high-frequency superconductivity? So we start very basically. Superconductivity is an ordered state, so we need to have an order parameter, and the symmetry of this order parameter gets very important. That's kind of how we classify this state, right? And so for superconductivity, the order parameter is called delta, is essentially proportional to the expectation value of a Cooper pair. So forming the Cooper pair here, and I have two indices here. So these are the quantum numbers for the two electrons, alpha and beta, and this would be the spatial properties and the spin properties, for example. So we are generally very used to think about if you take these two electrons and they form a spin singlet state, well then the spatial property needs to be S-wave because the superconductivity is a fermionic condensate, so we need to fulfill Fermi-Dirac statistics. But you can also have a spin triplet state, so now we are even in the spin index, and then we have to pick up this necessary minus sign that you need to have your fermionic statistics from the spatial parity. So here the P wave is the thing that gives you the minus sign, and here is the spin singlet that gives you a minus sign. So those are the two combinations we're used to, right? Now, there's nothing prevents you here from having a time dependence in this Cooper pair expectation value, and if you have a time dependence, well, Fourier transform will have a frequency dependence. And if you have this frequency dependence, you can be then even and odd in this frequency dependence. And at this level, what the oddness in frequency does is that it allows you to have other symmetries for the other parts of the condensate. So now, well, you can be even in frequency, and that will be the same as spin singlet and S-wave, for example. But you can also be odd in frequency, and then you can, for example, have a spin triplet S-wave because you pick up the necessary minus sign by switching a spin, which is by switching the frequency here. So you get a minus sign when you exchange the alpha and beta, because we exchange t to 0 in this case. So you get the minus sign from here, and so you can be even in the spin part and even in the orbital part. So this is sort of the very basic, the definition where the odd frequency comes in. So how can you think of this as an ordered state? Well, if you look at the BCS order parameter, that's really is taking the two times. So now you have t and t prime, and you take one t to the other, take t prime to t. So this is an equal time expectation value. And that would necessarily vanish for something that's odd in t, right? So the BCS order parameter has vanishing odd frequency pairing. So the question is, how do I define an order parameter? Well, one way you can think about it is, I want to be at equal time. So how do I do that? Well, I can take the time derivative, and we can argue if this is a good order parameter or not, but it's a convenient way to keep track of if things are odd or not, because if you take the time derivative and then let t go to t prime, well, this is only going to be non-zero if it's odd in frequency, because this per definition is zero for something that's even in frequency or time, and it's non-zero for something that's odd. It's only odd that has a finite derivative at t equal to 0. So we can use this as an order parameter if you want to, or a sort of a measurement of if you have this odd frequency correlations or not. Okay, so that's sort of how we can define it. Here is the one slide on the history. So apologies already for papers I left out on this slide. But the essential all began in as far as I know, 1974 by Berezinski, who proposed that maybe there is a spin triplet S-wave state in helium-3, in superfluid helium-3. And there you see it has to be odd in frequency, otherwise I couldn't have S-wave in spin triplet. This presumably was rather dormant for a while, and then in the early 90s, several people picked up this for superconductors who were proposing a spin triplet S-wave superconductor that was disorder induced. And here the thing is exactly disorder induced, because if you have disorder, then you presumably will only have S-wave. The other spatial parities will average out to 0. And if you then want to have it to be spin triplet, well, that has to be odd in frequency. Later was also spin singlet P-wave odd in frequency was proposed. And there was also some work done on heavy fermion compounds and the sense about writing these states as marijuana fermions. And there's a whole bunch of rather complicated models, for example, composite condensates. And there's also been a fair amount of question about stability of the state. Is it actually stable? And I'm going to skip all this, I'd say complicated here for a reason, because I want to talk about it. This is, I think, not fully resolved if it's going to happen or not. There's an intrinsic phase in the material where really the order parameter is odd in frequency. But what I'm going to talk about is instead where we start with a very conventional order parameter. We have some dull superconductor that just generates a Cooper pairing that we need, and then we look at what does the state actually look like. So this can, for example, be heterostructures where we take, for example, make a Josephson junction of some material, say, for example, the very noodle loop material I'm going to show later. Or, as I'm also going to talk about, we have multiband system where we start with assuming it's conventional pairing, but then we look at the pair correlation we can look at. And here, if you're interested in sort of more thorough reviews, there's at least two, I think, quite good reviews, one up later and one that's sort of in the process on the archive. Okay, so from now on, I'm going to talk about things. We don't have to worry about where the superconductivity comes from. It's there, thanks to some regular superconductor. And this is a traditional example of where you still get this odd frequency. So this is an SF interface. You have a spin singlet superconductor and a ferromagnet. And the spin singlet, well, this is the cartoon of the spin singlet pair. The electrons are clearly oppositely aligned. And in the ferromagnet, that doesn't kind of work. They want to be aligned in the same direction, right? So one could imagine that there will not be any proximity effect, that is leakage of Cooper pairing into the ferromagnet, if the spin singlet pairing is the only thing that it can be. But it turns out that you can go from the spin singlet S-wave superconductor to spin triplet S-wave, and then it's on in frequency. And this have actually, so it's actually measured, and there is a long-range proximity effect into F, so there's clearly our Cooper pairs going into the F region. The F region is many of the samples rather dirty, so it's a diffusive regime, therefore you assume that it always have to be S-wave, and then there's pair symmetry, nothing else that can happen, and it's odd in frequency. So the question is why, okay, so this happens, the question is how can we understand it a little bit more quantitatively? Well, we have to start thinking about what happens if you have superconductivity in a ferromagnet, and it's always, I think today it was a little bit on this, and maybe it's going to be later on in this school as well. But here is essentially a regular parabolic band, but it has an exchange energy, so there's more spin up electrons and spin down electrons. So we have two different Fermi surfaces. One that's bigger for the spin up electrons, and the one for spin down electrons is smaller. If you take this state and you still do spin singlet pair, where you pair electrons like this, it turns out that you actually get a modulation that's set by this big Q vector here with an exponential, and you can decompose exponential into cosine and sinus factors. So here you see you get some spin singlet pairs, but you also get the mixed spin triplet pair, and this is known as the FFLO state we heard a little bit about earlier today. So this is well known that this happens if you do superconductivity in a ferromagnet. So what happens in this interface is, well, this schematic is trying to explain this. So if you start with a spin singlet superconductor and you have a normal metal, well, the spin singlet can leak into the normal metal like this. There's no spin triplet. If you have something that's weakly polarized, the spin singlet goes into the mixed spin triplet, and then it starts oscillating. This is this cosine and sinus factors here. If you have something that's strongly spin polarized, well, it starts oscillating faster, right? The big Q is bigger, and it also, you lose some pairing on the superconducting side. This will be an inverse proximity effect, that you lose Cooper pairs, because a ferromagnet also influences the superconductor. And if you have something that's very strongly spin polarized, well, you can think about, well, you average out, these oscillations are so fast essentially that you don't get anything. So in a very strongly spin polarized ferromagnet, you will not get neither spin singlet or this mixed spin triplet state. Okay, that's not very encouraging, because I told you there's going to be superconductivity. Yes?
Sorry, but you're saying that on the superconducting side, you will generate, because you start from 0 pair amplitude triplet, right?
Yes.
So
Yeah. So this ferromagnet generates some spin triplet, and the mixed spin triplet can survive here, but they can't survive on this side. So this doesn't work. This ideal picture does not work. What we need to have is something a little bit different. So this was a picture I had in the previous page, the last one here. It doesn't work. But if you have an interface with another magnetization direction, everything works. Because now the spin singlet, before I was always in the C basis, but I can express a spin singlet in any basis. So let's pick the Y basis. So I do the spin singlet in the Y basis, and the mixed spin triplet in the Y basis, and then I put a field in the C direction. Then I can rotate, so because all three spin triplet solutions can rotate into each other. And then all of a sudden, if I express it in the C basis, I have up, and down. And now the up spin triplet pairs will survive in the ferromagnet. And these are the odd frequency state that survives in the ferromagnet and gives you a proximity effect in these junctions.
So can I ask a trivial question?
Yes.
What is odd frequency here in terms of notations? So far there's no frequency.
No. So this just assumes that everything is S-wave, and then it has to be odd frequency. We could say it's P-wave, it's very clean, and it's P-wave. But all the experiments, or at least sort of the early thinking of this, it was always so dirty that only S-waves survived. So what you need to have in this SF interfaces to get odd frequency, or get this equal spin triplet, is that you need to have some non-collinear magnetization. For example, two different magnetic layers, as in here you have something that is magnetic in the Y direction and in C direction, so different directions. You could have a spin-orbit coupled interface. So then you have effectively two magnetization directions in your sample tube, one associated with spin-over coupling and one with the magnetization. One can also have a helical ferromagnet where the magnetization direction changes. Essentially, you have to have some structure to your magnetization, and then you will get this odd frequency state. So here come some of the experimental signatures, and I should say, come back a little bit to the question here. Most things that are measured here measure something that is not directly probing the odd frequency state, it's probing all other properties, so essentially by method of elimination, the only thing that's left is that it's an odd frequency spin triplet S-wave. So for example, as already said, there's a long-range proximity effect measured in diffusive F. I'm going to show you on the next slide just one example. This odd frequency state often gives you zero energy peaks in the density of states. This was assumed previously to happen all the time. It actually doesn't happen all the time. There is some criteria on the state, so that's why I was written sometimes, but sometimes this can be a good initial guess at this odd frequency in the system. Paramagnetic Meissner effect is very often found in the system, and usually the Meissner effect is diamagnetic, means the superconductor expels magnetic field. If it's paramagnetic, means it attracts magnetic field. So this has been seen in these SF junctions quite recently. I'm going to actually show you in bismuth solenoid we get a diamagnetic Meissner effect, so it's not always true that all frequency give you paramagnetic. If you have a structure like an FSF structure, so the superconductor is rather small between two ferromagnets, you can actually change the critical temperature in the superconductor by playing with the magnetization directions and with the odd frequency. So they essentially say that the list is a little bit longer, but there's multiple experiments on all of these, and so I would say there's a large body of experiments supporting this odd frequency pair in these SF junctions. And to just give you one example, so this is on the long-range proximity effect. So here is, let's see, so here is a ferromagnet here, and it consists of a whole bunch of layers. So it's important to note that you have a cobalt here, and you have some layers called X here, and X is another ferromagnet, one of these compounds here. So when you don't have X, you just have the cobalt, and you just have one magnetization direction. And then the critical current in this junction here, going across this way, it drops exponentially. But when you put in this X layer, which has another magnetization direction, you essentially get a current that stays here, and it's, you know, on this scales of the junction, the current is essentially constant. Of course, if you make the junction very big, you're going to lose. You only have proximity effect as far as you have a proximity effect in a normal method.
What would be a direct, unambiguous measurement? Something non-negotiable, as crazy as it is.
Yes, I would love to find that out. Yeah.
We don't have that
No,
yet?
no, we don't know. Yeah. So part of the problem is that the odd frequency state, you can think, well, it's definitely a dynamic state, and it's also kind of hidden, because if you have something where you integrate over frequencies, it falls out. If you have something where you measure zero frequency, it's also zero. So you have to have something that's much more intricate in how it treats the frequency domain. And we have a couple of ideas we're working on, but there's nothing. I think it's a big, currently a big problem in the field.
Some Josephson thingy with a time.
So what I'm going to tell you in the very nodal loop materials is, if you just believe in spin singlet superconductivity, now if you didn't believe in odd frequency, you wouldn't think there was Josephson effect, and there is a Josephson effect. Again, it's not directly probing the odd frequency state.
So just to make, I mean, there are pi junctions, right, which can be made with distance.
Yes. So it's pi junctions too. I would say they are still not probing the odd frequency part. They're probing that you have spin singlet oscillating states. So yeah, I mean,
you need the sign change to get these pi junctions.
Yes, but you can think of this sign change as not necessarily tied to the odd frequency.
Okay.
Yeah, I think so.
So could I ask
Yes.
Andre's question again?
Yeah.
Because I think now we are allowed to ask stupid questions.
Yes.
I still
Can I
don't
provide a stupid answer? No.
So I still don't understand what is odd frequency about the state. Right now you just wrote down some wave functions and there was no frequency
No,
involved
no.
whatsoever.
No, so far it's been very hidden. It's essentially, I'm going to show you how it shows up, and actually you see there's an omega in the anomalous Green's function, for example, linear. But so far, just to get it sort of, to show that it exists, it's simplest well, to me it's simplest to understand it just that, okay, it's a spin triplet S-wave state, and that's not allowed. So therefore it's all equivalent.
So you're going to prove that in an experiment people see a spin triplet S-wave state in the absence of spin orbit coupling? Is that what you're going to? I don't know what I'm looking
Yeah, well, so this example shows that there is proximity effect despite you having a very strong ferromagnet.
Okay.
So, and this was presumably quite dirty, so then you would think it's just S-wave. It has to be spin triplet because it's surviving in a ferromagnetic environment. And then there isn't that many other options.
I mean, I don't know what the effect of dirt would be in this situation and so on. So why am I assuming it's very dirty and a P-wave triplet must be dead?
So yeah, I mean yes. So you will have to model this to see that, or as I said in the experiment, assume it, or measure something that shows that it's dirty. In the example I'm going to show will be actually calculated. We can actually, the P is identically zero because of symmetry actually.
But also you're ignoring spin orbit coupling, because as the minute you put in spin orbit coupling, this distinction between singlet and triplet will also go away.
No.
Well, I can still think about it. I can still say I have a spin singlet S-wave or spin triplet P-wave because of spin orbit coupling.
No, singlet triplet is not a good characterization.
But I can say, well, yeah, but if I'm willing to take them into mix with
Because
each
there's
other,
no
right?
parity, you're saying, or what?
Yeah, I mean it's
Because there's
even
no parity.
parity. Yeah, it's even parity or not parity. That's a
Yeah, this is
perfectly
a distinction,
reasonable
clear distinction.
symmetry allowed distinction.
Well, but I can still think about it in these two. I can still decompose it in those two channels, and I have to treat them at the both combo. Yeah. Okay. Well, let me jump from the SF junction to the SN junction and show that actually there's odd frequency in this system too. And now what happens here? There's nothing touching the spin part of the condensate, but I do break translation symmetry. So what can happen is my spin singlet S-wave state can actually go to a spin singlet P-wave state, and then it needs to be odd frequency. This is actually a calculation showing the order parameter and the S-wave spin singlet. So everything is spin singlet S-wave, and there is a P-wave component here. This is leaking into the superconductor. And this P-wave component, as well, it's not displayed here, but it is, if you look at the frequency dependence, is odd in frequency. Since this is P-wave component, now coming back to if it's dirty or clean, this is only been presumed to happen if you have high transparency junctions. So if you have junctions, it's not very transparent, this component is essentially killed. We could take these two, so in this system we broke translation symmetry and we went from S-wave to P-wave, and we didn't touch the spin, so both spin singlet. If we do this in a topological insulator, we actually couple momentum and spin, right, through the Dirac-Hamiltonian K dot sigma. So what can happen then if you do, say, a junction on, so this is actually a 2D TI, and we put a superconductor, and this is just the helical edge state here, and then you can actually get spin triplet S-wave pairing that's odd in frequency. So now I can touch the spin part on my condensate because I have a spin orbit coupling. And this is a calculation of the even in odd frequency interface components going into the superconductor. We see the even frequency interface component is essentially zero at zero frequency, whereas you have an odd frequency component here, and you see that this odd frequency is actually following exactly the same trends that the density of states up here, and it turns out the odd frequency pairing here generates finite density of states on the S side of the junction in the topological insulator. But with that, let me just summarize. So this is things that I think is fairly well established. It happens. So the odd frequencies essentially is dynamic and hidden pair correlations. It's well established in this SF junction, and you get odd frequencies spin triplet S wave. It gives you a long range proximity effect into F, so you can still build Josephson junction with ferromagnets. But it will also happen in junctions where you don't have any magnetism and you don't have any time reversal symmetry breaking. And if you have spin-orbit coupling, you can get spin triplet S-wave symmetry as well. So note here that these are odd frequency state and there's no time reversal symmetry breaking. So these are two different concepts. So being odd in frequency means you're odd in a relative time, and that's not the same as being odd under the absolute time. So odd frequency state do not need to break time reversal symmetry. Okay, so with that, let me go into an example, but hopefully the fact that it's odd in frequency will be very clear. So we were interested in this veiled noodle loop semi-metal, so let me just give a quick introduction to those. So here is just a display of different types of Fermi surfaces. So in a metal, we have a finite size Fermi surface. In the insulator, we don't have any Fermi surface. And the Dirac material is kind of in between, right? We can have point Fermi surfaces. If you get rid of your degeneracy, you get what's called a veiled semi-metal. If you have a degeneracy, we call it a Dirac semi-metal. And if this point here, instead of forming a point as a Fermi surface, form a little loop, then we call it the veiled nodal loop semi-metal. So that was trying to illustrate here. So these are the materials we're interested in. There's form a little loop here. So what's so special about them? Well, the veiled semi-metals, as you might be familiar with, they have these veiled points in the bulk. And if you project it on the surface, you get a Fermi arc, essentially a state sitting at the Fermi level that connects the two veiled points. In the nodal loop material, you take this loop and you project it on the surface, and you actually get a whole state that sits at zero energy. So this would be a flat band sitting at zero energy, something called a drumhead surface state. So it's topologically protected, it has to be there. And it can buckle a little bit, but it should sit there. So this is just an example on the model we're using to show that you have a density, a very short peak at zero energy from this surface state, so this density state on the top surface of a slab. And it also, in magnetic veiled nodal loop materials, will be magnetic. So this is fully down polarized on the top surface, and the bottom surface will be fully down polarized. So this is the model that we use. It's not particularly important. The only thing to notice is that we have both spin-orbit coupling in the bulk, and we have spin polarized and drumhead surface states. Because those are two ingredients we need. And it can also regulate the doping. So at zero doping, we will form just a nodal loop. But if you dope the material, this will form a donut Fermi surface. So we're not particularly sensitive to the amount of doping in this material. So this is showing the band structure. So here you have the two veil points, and with a flat band here. So we have one of these states sit on the upper surface and one sits on the lower surface, and here again is the density of states that is, so it's down on the first surface and up on the lower surface.
You say it's topologically protected. If I were to include some weak interactions on the surface, wouldn't they lift this degeneracy?
Yes.
Okay.
Yeah, likely, because it's a peak in density state, so you can get an ordered state on the surface.
Yeah.
Assuming we don't get this.
Okay.
Well, in some senses, it is actually already spin polarized, in that sense you already have magnetization there. But you can induce another order
Right,
as well.
all kind of order
Yes,
you can
yes.
that. Yeah.
Yes. Okay, so what we have now is we have a material, we have a fully spin polarized surface. It's fully spin polarized, we really should have no spin singlet pairing in this material. So then one would assume that you could not get any Josephson effect. If you were to build a Josephson junction on this material, there would be no Josephson effect if you use any conventional superconductor. That would be sort of the logical step to take, so well, if it's fully spin polarized. So we say, okay, well, we think there's this thing called low-frequency superconductivity. Can that help us? So we modeled this system. So we took our wave, nodal loop material, put it next to two superconductors, and we solved this in a big lattice, essentially. And these arrows here just indicate how the spin winds through the structures. The spin polarized here, it winds through the spin overcoupling, comes out the spin polarized on the other surface. So what do we do in practice? Well, we have the Hamiltonian. So we form the Green's function, and the Green's function has the normal state here on the diagonal, and the anomalous state, that is the pair correlators on the diagonal, the off diagonal. So we take these and we just look at these. These will be our pair amplitudes. And it turns out, if you look at these, you solve it, you will have some spin singlet S-wave states, because that's what we induce from their contacts. We will have odd frequency triplet S-wave state. And we will have in plane P wave is exactly 0, it's cancelled. We have some between the planes, but that's so low because it's proximity effect into each layer, so it's exponentially suppressed. And here is the results. So these are the S-wave amplitudes, so this will be the spin singlet and the odd frequency. So we divided up, each color is for a different spin channel. And now you see that some of them are odd in frequency. This blue here, well, the blue too, but the red one is odd in omega. Whereas the dashed one, which is a spin singlet, is even in omega. So the dashed one is a spin singlet S-wave, and on the surface we have some of that because it's rather naturally. I put a big superconductor that is spin singlet next to it, so in the first layer it is allowed to be, but then this dashed line essentially just disappears when I'm moving through the material. And instead, the only thing I have is spin down polarization, where was the polarization I had on the surface. So this is the real part, and this is just the imaginary part. And you see they have the same symmetries. So the only one thing that survives inside here is the odd frequency equal spin triplet S-wave amplitudes. And it's really the same story as in the SF junctions, because what we have is we have spin polarization and we have spin overcoupling. So I have two different magnetization axes. It just happened to be in one and the same material. I don't have to engineer my interface by putting a second magnetic order. Everything is in the material. So then we looked a little bit more into what happens to this pair amplitude when we move
Can I ask
into
a quick
yes.
question? Sorry to interrupt,
Yes.
but just for understanding of a couple of us.
Yeah.
Normally, when you write down equation for anomalous green function, it's just the same as gap equation. So there's a quantity delta that depends on frequency. You get F, which is odd in frequency. And the question is where it comes from. In a situation when there is no time dependence in your interactions. So where is it?
Well, it comes from, so H here has no time dependence, but it comes from this omega. I mean, I get an omega dependence here and I take the inverse and it shows up here. That's a quick and dirty answer.
I guess maybe I can try to ask the question in a
Yeah.
different way. That usually if I do just BCS theory, then I never have any frequency dependence to that function and so on. The only time I do get a frequency dependence to that function is if I do something like Eliashberg theory, where the interaction itself is retarded. I guess Andre
We're
is
asking
asking,
the same question.
where is that frequency dependence in the interaction?
So this will happen because I've done something, so in this case it happens because I have some inhomogeneity. In this case I have inhomogeneity in real space.
But it's real space, not time domain.
Yes, but that propagates through. So I have a superconductor and I propagate the Cooper pairs into this material. There's no order parameter in here. The order parameter sits out here. So you will have a frequency dependence even in an SN junction.
But which equations are being solved, so obtained, maybe to put it this way?
Yes, so the equation being solved is I take this Hamiltonian for my wave nodal loop material. That is Hamiltonian here. Here I have a single band superconductor with an order parameter. S-wave, I mean, it's just delta with a phase, so I can have a Josephson current. And I put that together with a tunnel coupling, T, and then I solve it. So that is my Hamiltonian. The Hamiltonian has many sites. and then I just get the Green function.
So there's a proximity-induced solution that if you allow for a frequency dependency, does have a frequency dependency,
Yes.
and it's just of that type.
Yes.
Okay.
Yes. Yes.
So that's in real frequency, is this the retarded anomalous Green function or?
Yes, this is the retarded in advance, and you have to be careful when you actually do it for negative frequencies, so it shows up. See, sometimes we do it in the Matsubara too.
But so then in DCS, let's say perfect delta function peaks, and you get a spectral function which is the sum of two terms of both valuable. And then for the F, you always get a minus sign because it's always odd.
Yeah. Okay. Okay. But so let me just tell you quickly here, because I want to move on to the multiband too. So I have the spin triplet that survives into the material, doesn't matter really with the doping. And let me just compare with if the metal inside was a normal metal state, then I will have this would be the normal proximity effect, the spin singlet. These are two examples of sort of the traditional junctions. Odd frequency junction with a half metal with no proximity effect if you don't have two magnetization directions, and if you have two, so here you have magnetization plus a spin active interface, you get some spin triplet magnitude, but you see this one is much lower than this one. And that shows up really when you look at currents. So these are currents as function of various parameters, doping, delta, and this coupling between the material. And the VNL is the blue line, and you see it's a much higher current than the normals. Let's see, the normal one is the dashed line, so the VNL is quite high current, and there's no spin singlet pairing, and there's no even frequency pairing in the junction. This current is carried by the odd frequency correlations. And if you look at traditional odd frequency junctions, that would be this yellow line, and you see the blue line is much higher. So it's a huge current, and they attribute this because you have to the flat drumhead surface state. So you get very good contact between the superconductor and the veiled material because you have this drumhead state sitting at the surface. So this is your summary. You cannot have any conventional superconductivity, but you have odd frequency equal spin triplet superconductivity, and it gives you a huge using power, much bigger than been seen before. Okay, so let me spend the last minutes talking about multiband system. So here the story is slightly, the story is similar, but enough different. So this gives you odd frequency pairing in the bulk. So what happens is that you get another index to play with. So now alpha and beta is not just spin and parity, it's also band index or orbital index as well. So now you can, for example, be spin singlet S-wave, it can be odd in frequency and then be odd in band, and this is still satisfying for metric statistics.
Sorry, what do you mean odd in band?
That means that this is a pair between two electrons that live in different orbitals and bands, and when you write that, that can either be even and odd, as say you can have 1 and 2 plus 1 and 2, or 1 and 2 minus 1 and 2.
Okay. And is the same if you use band or if you use orbital, or?
Yes, I'm going to interchange in use band and orbital in the end. I'm going to show that can be replaced with valley dot wire, take your pick of some other index. So then you actually have a classification that you can call spot. So you have to think about what is your spin, what is the spatial parity, what is the orbital parity, and what is time, and it needs to be -1 upon this. So you can make a little table. This again saying if you have a spin singlet and you have you can be even in parity, and you can be odd in time and odd in orbital, or you can have spin triplet, and you can be spin triplet p-wave with a minus odd in time, odd in orbital, for example. But there's 8 different classes. So that means it's allowed, but does it happen? So this is going to show you that it happens. This is a simple 2-band model. So I have band A and band B, and a pair in both bands. So no frequency dependence here. But then I add a hybridization term. So it's a single particle coupling between the 2 bands. I take this part, the normal state, and diagonalize that. So I get 2 new bands, C and D, fully diagonal. I get pairing that is intra-band, and I also get an interband pairing. This is just a rediagonalization. The interband pairing looks like this. It depends on gamma, of course, and also depends, you have to have different order parameters in two bands, but otherwise it's non-zero. Now, so now I'm not going to deal with frequency. Now I'm going to look at wheels in time here. Later I'm going to show you in frequency too. So I can create a pair correlation between C and D that depends on tau. So tau is my time here. So it can be even, then it's the plus sign, and if it's odd, it's the minus sign. So the even one, well there I can just take tau to 0 and it's going to be non-zero. So this is my even frequency, even interband pairing. But they can also take the odd combination with the minus sign, and that's going to be 0 if tau goes to 0, per definition. But I can take the time derivative, as I told you before, I could use that as a proxy for the order parameter for the odd frequency, and then let tau go to 0. And that would generate an odd frequency, odd interband pairing, if it exists. So let's see if it exists. I take some same band structure, different order parameters. I rediagonalize, and the reason why I pick these, the delta A is minus delta B, is because I only have interband pairing. I diagonalize, I solve, and the FE, so the even part, just gives you the BCS equation, as you would expect. The odd one is actually non-zero, and it is the even one times I gamma. And it is odd because that was kind of how it's defined, is with a minus sign, so it's odd in orbital, and it's also is a time derivative. So it's odd in time, otherwise it would be 0. And this was for a particular values. This just shows that this happens at all values. And this I is actually important. The I means to actually preserve time reversal symmetry.
But the function itself is even function of frequency, is just imaginary.
I'm sorry?
The function itself is even function of frequency. It's just
This
an
one.
overall factor of I.
No, because his FO is defined as a derivative. Here.
Derivative is even.
So the derivative is even, but then the thing that before I took the derivatives off. But let me show you, maybe this show me exactly the same model by solving with perturbation theory. So again, I have the same term, and I can now look at interband pairing as forming. So this will be the anomalous Green's function band A. You have a scattering element coming from here, and then you just propagate with a G2, and there's 2 of them. And now I can, there's a quadratic Hamiltonian and sum to infinite order, and I can define an odd interband, so F12 minus F21, and it shows up with an omega. Now you can show the even one, and it shows up with one. It's even in frequency. D is depends quadratically here. So here you get the omega dependence coming out there. With no, I didn't start with any omega and delta 1, so it's really just mixing the bands. Okay, let me quickly show that this has some consequences in Sr2RuO4. So there haven't been a lot of talks on Sr2RuO4, but it's essentially, what's important for what I want to say is it has 3 orbitals, XY, XZ, and YZ, and they form 3 bands, the gamma band, the beta band, and the alpha band. And this has been coming up as being controversial. Is it spin triplet? Is it not? Actually, I'm going to assume it's a spin triplet chiral P wave, but everything I say it goes through. If it was spin singlet, that's way too. The only thing is important is break time reversal symmetry, because I'm going to use the Kerr effect. So the Kerr effect has been measured in Sr2RuO4, and just to give a crash course or crash slide on that, you measure reflected light, and it changes the plane of polarization when it gets reflected, and it's primarily measured when you reflect light on magnets, so it seems to be a signature of time reversal symmetry breaking. But it was found in Sr2RuO4 too when entering the superconducting phase. So here showing the superconductive resistivity coming down here, and here is the curve, this rotation angle. You see this, it's in nanoradians, so it's really small, but it looks like it's statistically significant at the measure coming up here. So that was assumed as a big point showing that Sr2RuO4 breaks time reversal symmetry in the superconducting state. But then later on was shown that if you actually have a single band chiral superconductor, it will have a zero Kerr effect. And then said, oops. But it turns out if you have interband pairing, when you have some relative superconducting phases, you still get a non-zero Kerr effect. This is the interband process is exactly the ones I've been talking about. So what we did was we said, okay, so let's just put up a very simple model for Sr2RuO4 and see what we get. So we used two band models. We just took the alpha and beta, the XZ and YZ orbitals upon the alpha and beta band. And we assumed some pairing. As I said, this could be spin singlet 2. So here is my my normal state, the interorbital energy, the interorbital hybridization. We assume some intra-orbital pairing and some interorbital pairing. And then I work out what is the odd frequency pairing, and it turns out that, well, I have an odd interorbital pairing, and it's clearly odd in frequency, has the omega here. So it's one term that comes because I have an interorbital hybridization, a gap asymmetry, and I have some interorbital pairing, and it comes because I have a dispersion asymmetry. Now, we were fortunate that Taylor and Callan had worked out with the same model the Kerr effect. So we compared our expression here with the expression of the Kerr effect, and it turns out the Kerr effect would only be non-zero if I have some interorbital hybridization, this epsilon 1, 2, plus some gap asymmetry, or if I have interorbital pairing, delta 1, 2, with some orbital symmetry. And if you, well, it's not exactly the same form, but if you stare at this and you say, okay, I know this is non-zero, that is what the measure, then if this is non-zero, then this must be non-zero. So we're saying if you have an intrinsic Kerr effect, you know that you have odd frequency pairing in your system. You can do this with a 3-orbital model too. In the interest of time, let me just say that it works out, and you have the same. You can actually compare with a similar expression with Kerr rotation. It's a little bit more complicated, but it all works out. And if you just want to look at what it looks when you plot this in reciprocal space, so here's pairing on each of the 3 bands, band 1, orbital 1, 2, and 3. Here's the even inter, and this is the odd, and you see it's small. This I have to take this up 100 times. So the odd frequency state is small in Sr2RuO4, but if there is an intrinsic Kerr effect, it must be there, and the intrinsic Kerr effect is small. So
earlier on, when there was a lot of pressing for like, what is the smoking gun evidence of odd frequency pairing, you were very hesitant. You said, there isn't really anything. Isn't Kerr effect?
Yes. So in this multiband system, I would say if you measure the Kerr effect, an intrinsic, I should also say it's an intrinsic Kerr effect, because there has been work saying, well, maybe if you have a dirt in the material, but if you know it's an intrinsic Kerr effect, then yes, then that would be a good. But again,
but excuse me, but how you know it?
Yes, so here is the thing. I'm comparing the expression of the Kerr effect with the expression of the odd frequency. So in that sense, I can't really say that odd frequency is generating the Kerr or the other way around.
No,
I'm saying it depends on
somebody
the
measures Kerr effect. How you know that it's extrinsic rather than impurity?
Yes. So that's one caveat, and the other one is sort of if you want to say the odd. I'm not saying the odd frequency is causing Kerr effect. I'm saying they're coming from the same source.
Right.
They're coming from these interorbital processes and materials.
So do I understand it correctly? What you're saying is if there is an interorbital pairing, although we typically don't think about the frequency-dependent part because we only do the equal time, the part that you now assign as even frequency, that's what we do and we just stop there. But if we now, being enlightened, further go on and also look at the time-dependent part, we are going to see that other component.
Yes, that's an excellent summary. Yeah. So what I'm saying is it is this component here. It's Sr2RuO4 and it is small, but the Kerr effect will measure it.
So is the fact that the Kerr effect be done at finite frequency, is that somehow responsible for the fact that you're able to pick up the odd frequency pairing?
I don't think so. I think this expression comes.
Because you had said that at omega equals 0, actually the odd frequency pairing doesn't show up. That's what you had said.
Yes. On the other hand, the calculation for the curve, there's a reason why I'm not showing it in this room, and it's
I think
it's rather
an
messy.
interband optical transition that would be the signal band simply not there, and therefore.
Yes, so it's something at finite
I think that's more to do
energy.
with
Yes.
the interorbital
Yes,
story.
yes, yeah. Okay, so sorry for going through this a little bit fast, because I want to come and definitely talk about this, because this is a material that actually have a lot of odd frequency. This thing is 10 minutes, right?
10 more minutes.
Okay, excellent, good. There it comes. So this is a material that actually I'm going to show that the odd frequency is not small, the contribution is actually dominating the even frequency. So let me just go through, because this, to see what's happened here. So we heard a little bit about this in several talks today. So this is just repetition on this. So you take your topological insulating bismuth selenide and you dope it with copper, strontium, and niobium, and it turns out it's an intrinsic superconducting state. So you can think of this, you have a topological insulator, it's for insulating, you dope it, so your Fermi level ends up in the conduction band. So now we have a metal, but it turns out it becomes superconducting. The normal state belongs to the D3D symmetry group, so it has a threefold symmetry. Nonetheless, in the superconducting state, they measure a very clear twofold symmetry. So this is just one of many examples. So this is the upper critical field, and you see there's have a clear twofold symmetry. This is a polar plot showing that there certainly is no threefold symmetry left here, but it's a twofold symmetry left. Okay. Now, if you take this, so the question, okay, so how do you work with this? Well, we take the simplest possible normal state Hamiltonian for this material. So this would just be a doped topological insulator. You have, so here you recognize that this is the essential, the direct spectrum. You have some orbital, because you have topological insulator have two bands, so you have to come from two orbitals, right? I have a hybridization between my orbitals here. So sigma acts in orbital space, so this is an orbital hybridization, and this is just a doping. And if you look at the energy spectrum is Hamiltonian, you see the doped direct spectrum. So you have an anisotropic Dirac cone here. So as in plane is symmetric, but then you have another velocity in the z direction. And the m here gives you the mass, and then you have some chemical potential just dope in and out of the mass. Okay, so that was a normal state. I think that's rather uncontroversial. Now, for the superconducting state, if you assume you have a k-independent order parameter, and as far as I know, everyone has so far assumed that in this field, and we know that we have a nematic state, then the order parameter has to belong to a 2D reducing representation called EU, not the European Union, but an odd representation. And now it's k-independent, so this is an odd representation, but it's k-independent, so this is not S or P wave, but it's actually odd in an orbital index. So it will be a combination of these two, so that this is 2D, it means that it has two basis vectors spanning the space of the order parameter. And you see they are spin triplet, they both point either up or down, and 1 and 2 are the two orbitals. One can write this out and say, okay, so which combination do you get? You don't have to get into detail of this, but this is the orbital part, this is the spin part, and you can write, you essentially have a component AX for one of them and AY for the other one. And for the nematic state, it would be a cosine of some angle and a sine. So you can pick any angle, and this would still be the nematic state. What's important here is this is it's an S-square state, because I didn't have any K dependence. It's a spin triplet state, you see that here, this up or down, and it's odd in the interorbital index, that you can see from the sigma y in here. So it's an odd interorbital spin triplet S-square, and that still works, right? Because this is even, you have plus here, and you pick up a minus sign here, so it's
But when people say it's K-independent, they mean in the original orbital language. In the band language, this is a strongly K-dependent state that is odd in K.
Yes.
And that's what we usually assign in the momentum basis when we talk about K even in odd states. So.
Yes. Yeah, I just wanted to sort of, because if I say it's odd interorbital spin triplet, you might say, okay, but what happens in S or P way, right? But this sort of means it satisfies the spot criteria.
Yeah.
Okay, so this is actually odd interorbital, and that's it's a very strange state to actually have that. But the fact that people are measuring being nematic means I think it's a good chance that it actually is the state. Okay, so we took this state and we did the same thing as we did for the Raynoda loop material. We looked at the Green's function, the anomalous Green's function, and we looked at all different pairing amplitudes listed here. I'm not going to bore you with all of them, but let's just point out that this is the order. This is, I assume, this order parameter. It was S5 odd interorbital and even in frequency. The correlator just looks like this. But there's also a term here. It's odd in frequency. And it's intra-orbital. So this would be the type of pairing you most normally would think of, that you have pairing inside an orbital, not in between orbitals. But to have that, you actually have to be odd in frequency. And it's generated by the intra-orbital hybridization. You need to have this end there. Okay, fine, it's there. But then we looked at, what are the sizes? So this is taking DFT band structure for the doped TI and the experimental relevant gap size, and it turns out that the red one is the odd frequency. This is the amplitude. That's why it doesn't look odd. Sorry, this is a magnitude. And you see in this regime here, essentially the gray regime here, the odd frequency is actually bigger than the even frequency, a rather large range of frequency. I could also look at the in-plane P wave, and the same story that goes there. The odd frequency is bigger than the even frequency. So over a rather large range of frequencies, the odd frequency is not small here. The odd frequency is actually very big. It's even bigger than the assumed pairing that we had. Do you have another minute?
You have 3 minutes and 54 seconds.
Oh, and I will talk really fast. No, I will not. I will just show you. This gets a little bit technical, but let me just tell you about the Meissner effect. So I said before that a lot of odd frequency gives you paramagnetic Meissner effect. So we calculated this for this bismuth cell, and I was thinking, okay, so dominating odd frequency, maybe this is paramagnetic Meissner, and that wouldn't be very good. Because then why is it superconducting? So we calculated the current response to the external field, so we introduced this K tensor here. And the Meissner effect will just be the static, the response to static uniform fields that take the frequency to 0 and take the momentum to 0. Now the TIs gets rather complicated. It took us a long time to actually figure out. You can't just take your textbook thing here because there's no diamagnetic current because it's a linear K spectrum. And also the current operator is off diagonal in spin space. So we have essentially all complications you can think of here, almost. But nonetheless, we can calculate the superconducting part of this current response, and it's going to come down to one that just depends on the even frequency contribution and one that just depends on the odd frequency contribution. And in a traditional, very simple multiband superconductor, this one will give a diamagnetic contribution, and this would actually give you a paramagnetic contribution. So now you can imagine then, okay, so this one is big, maybe everything is paramagnetic, and paramagnetic means you are attracting magnetic field. But it turns out that actually this band, having these two bands or two orbitals, actually makes things much more interesting, I would say. So this is the Meissner effect from the even frequency. You see, and a lot. Well, it's first of all bigger, but nonetheless down here in very low filling regime, the odd frequency can be bigger, but you see the dashed and the solid line are essentially on top of each other. So that means they essentially cancel because they come with different signs. So here I've plotted the amplitude, and here are actually the signs you should have. So the even frequency, if it is intraband, an intraband process is positive, that means it's diamagnetic. But if it's an interband process, it's actually paramagnetic. And the odd frequency has the opposite behavior. So the intra is indeed paramagnetic, but there's a large contribution from interband transitions for the Meissner effect. So even though we have a lot of odd frequency correlations material, we actually get a diamagnetic Meissner effect because the odd frequency have a lot of contributions to the intra, this interband part. So this order parameter really seems to work. It has the correct Meissner effect. And as I said, the Meissner effect, I'm not showing it here, but you will see the nematic state in the Meissner response as well. So with that, let me just summarize on the multiband superconductors. So if you have more than one band, if you have 2 bands or 3 bands, or orbitals, as long as you have processes that take you between these bands, you will very likely have odd frequency correlations in the material. I showed this as a fact in Sr2RuO4, and there, if you have an intrinsic Kerr effect, that will actually signal the odd frequency. And then I showed that you have dominating odd frequency pairing in the bismuth selenide, and actually the odd frequencies, what we usually think is a more standard pairing, is sitting inside each orbital instead of being between orbitals. But even if the odd frequency dominating is actually a diamagnetic Meissner response. Now, as I mentioned earlier, I can change this band or this orbital index to, I can call it layer, I can call it vires, I can call it dots, or I can call it valleys. So for example, if you have a system with 2 valleys, you can have inter-valley pairing, this is odd in this valley index, and you have odd frequency pairing. So it's a very generic concept of introducing another index in this superconducting state. So with that, just let me put on this whole summary slide, and I think I just leave it there. Thank you for your attention.
Questions? Yeah.
Yes. So the fact that it's odd in frequency, does it has an effect on the coherence length? Like, is it more sensitive to disorder, or?
Well, the short answer is I can't answer generically. The generic answer is I don't know.
Okay.
In a lot of these proximity structures, it's essentially depends do you have proximity effect or not, and it becomes sensitive to disorder only if it changes the spatial parity, if it goes from S to P. But if you assume it, if you know it's S wave, then it will not be sensitive to disorder.
Yes.
In the last part of this selenide, is that been measured experimentally because of diamagnetic Meissner effect?
We looked into it and we couldn't find any measurements of the Meissner effect.
When you mean
Meissner effect is certainly diamagnetic.
Yes, exactly. But if you measure, because the Meissner response would also have the pneumatic, rather natural maybe, that it will depend, but it's only direction. Yeah.
Some group measured it.
Oh, they did. Okay.
Yeah, in Hong Kong group.
Yeah, they measured the.
Yeah, the magnetization.
Okay.
Yeah.
Okay. Yeah.
Andre.
Let me ask a question in a slightly different way. It's motivated by the stuff I was doing with Oscar Wafik when we looked at pretty much the same stuff. If you consider interorbital pairing, if you go into band representation, I guess the pairing that you want to have will be also interband pairing. Then you have a problem that at weak coupling, you will never put both particles on the Fermi surface, and so you will never get Cooper logarithm in a normal way. You can cure the problem by adding spin-orbit coupling, but then, as one said, difference between triplet and singlet become murky. So, do you have an answer how to overcome this?
Yeah, so we had exactly, when you first come up with this, just a simple two model, orbital models, like, okay, it works in a theory game, can we find it? So then we started looking around to what multi-orbital or multiband systems are there, and I think the fact that in Sr2RuO4, if you believe in the intrinsic Kerr effect, it has to happen there, that you have a little bit of this interorbital process. If you believe in the pneumatic state in bismuth selenide, and it is really this odd the only pairing that consistent with group theories is odd interorbital pairing that gives you. So I think I agree with you. On the other hand, if you complicate the normal state enough, you can still get it. For example, these topological systems, I think, is a good example where you really always have two orbitals. I mean, you can't get two bands without having two orbitals, and they're intrinsically mixed. And you also mix the spin parts, right? Because it's often k dot sigma or something. So my answer is yes, I agree with you, but I think there are counterexamples where it seems to actually work. Maybe TC will never be very high in this material, so, as I said in the beginning, this is not probably high TC stuff, but low TCs seem to happen.
I didn't quite. So is there a model I can write down where I have a Cooper instability that gives rise to odd frequency pairing?
As an intrinsic phase.
Yeah.
Yes, there are these composite condensate that exists.
Composite means there's some spin operator involved.
Yes,
in
you take your
pairing.
Cooper pair and you add another bosons, and those I
Yes.
think are, people agree that these will definitely be stable.
And there's a Cooper instability as well. There could be.
What do you mean by?
That there's an arbitrarily weak value of a certain interaction and instability to the thing.
That I don't actually know. I haven't actually worked, so I mainly work on this where I say, I get superconductivity from something rather dull, and then I look at what's actually superconducting state look like. But I suspect someone has an answer to that, but not me.
Further questions? Yes.
Yes, this is a question I had a few slides ago.
Yeah.
In order for the spin triplet component to survive through the interface, does it need to be coupled with the spin orbit? I didn't understand that very good.
Yes, so what happens if you just have an SF interface, so you just have one magnetization direction, the most you can get is the spin singlet transferring into the spin triplet with mixed spins, so they said zero channel, there's a spin triplet that still look like this. And if you want to get the spin triplet with both spins in the same direction, the thing that's going to survive in the ferromagnet, you need to have another magnetization direction, so you can either have, say, a multi-layer magnet, so you say one magnet points in one direction and one magnet points in another, or you can have spin-orbit coupling in the interface, because in the spin-orbit coupling allows you to go to the mixed spin-triplet state, and then the ferromagnet will offer the second sort of twist into the equal spin state. So I think a lot of systems that you looked at now have that spin, because spin-orbit coupling tends to appear at interfaces, and if it's strong enough, it will work very well for this transformation from spin singlet to spin triplet.
Thank you.
Further question? I still got one. You said the most natural thing is intra-orbital pairing. In my naive view, I would say I don't care what orbitals my states on the Fermi surface are made of. I look at my Fermi surface, and then I'm looking how I can pair a state at k and minus k. At least at very weak coupling, so whether it's mixed of orbitals or have a pure orbit. Orbitals is just some chemistry language, not even good quantum numbers. Right? Good quantum numbers are momentum states, plane waves, and so forth. So why is it the most natural thing?
Yeah, no, I will agree. So if you think, so I guess I will call it a little bit with the description used from Sr2RuO4, sort of thinking pairing in the orbitals. But if you think this is a weak coupling, then I would agree with you. And I probably shouldn't use the word most natural, but still sort of.
In some strong coupling language, I can see that. At weak coupling, it's perfectly natural to think in terms of the bands and the good
But nonetheless, I think we are not so used to thinking about something that's odd in some interorbital. I mean, at least when this state was proposed for bismuth selenide, it was one of the stranger combinations that people really had to find a nematic state to believe that was happening.
But I guess we all are asking the same question, that you can get interorbital pairing. This is perfectly okay. But if you look at the band language, and as Jörg said, you have fermions with k and minus k. The question is there any interaction within one band that would give you what you call odd frequency pairing?
Within one
band.
No,
The
if
ones
you have
such that both fermions k and minus k are simultaneously on the Fermi surface.
Yes, if you have one band and you don't break any symmetries, no interfaces, nothing, you will not have odd frequency. You always need to break some symmetry.
Suppose you have many bands, and you consider multi-orbital system like iron-based, whatever.
Yes.
Question is there any leakage of multi-orbital pairing of your type onto pairing of two fermions from the same band?
Yeah. So in terms of, I haven't looked a lot into the iron-based superconductor, but I had Brian Anderson look into if there was some of this, and he said that they had some of this, they required odd interorbital pairing in his, I think, 5-band model, and he had some odd frequency component. It was small, so we never did anything with it, but it was there.
I
how
guess
it's
it was
big
weight
enough.
spin orbit coupling. Then you get it.
Yes, yes, you don't need spin orbit coupling. I don't know if he had, this was a few years ago.
I'm pretty sure, yeah.
Yeah. So my answer on the iron base is that, yes, I think it's there. If it's important, it might be important in the compounds that has a lot of orbital, where the orbital character becomes very important. I think there might be a good place for that.
Very well, there's another one, yes.
The last case, the bismuth selenide case, where the pairing is intrinsic, can you write some kind of BCS-like equation, wave function?
For the odd frequency part?
Yeah, with all the pairing coming from.
Yeah, so, well, so we still assume that the order parameters at even frequency. The short answer, I don't know, but I don't know really what I should use it for, since I assume in the order parameters frequency independent property. Yeah, I don't know.
Okay. No more questions, then let's thank Annica one more time.